Good morning, everyone. I am Joseph Appertey, and I'm here to present to you on the topic environmental burden predictive tools for the controlled environment agriculture industry. This work is being supervised and then by Dr. Aaron Wemoff, and then also the funding is provided by the Environmental Protection Agency, USA. The presentation cut across 5 main chapters. We have the introduction, the literature review, overview of the tools, use case of the tools, and then conclusion and recommendation. So controlled environment agriculture environment is an indoor type of farming which maximizes crop growth and then reduces the environmental footprint. The various types that are being practiced are the vertical farms and then the greenhouses. And based on this, it will require huge amount of energy usage and then high amount of water usage. So an image here simply shows environmental greenhouse control environment agriculture for cultivation of some plant. So with the vertical farms, we say it's a system of farming whereby plants are grown in a vertically arranged system to minimize environmental pollution and also improve the resources available by applying advancement system of irrigation, which is a drip system. And the various techniques that are being applied include the hydroponics, the aeroponics, and then the aquaponics system of vertical farming. So the greenhouse is a semi-automated system which optimizes plant growth and is dependent on the system design and the orientation to allow enough sunlight for the plant growth. These systems also requires the heating for low ambient temperatures and then the cooling for excessive heat. So an example of experimental greenhouse is shown here. And then the various footprint types, whereby we have the carbon footprints, the scope 1 and 2 water footprint, then the water scarcity footprints, and also the green, blue, and then the gray water that are being applicable in these operations. The key environmental metrics to be considered include the available water remaining, which quantifies the availability of water to the demand in a particular region, and also the energy and then the water intensity factor, which describes the amount of water consumed to generate electricity, and then also the scarce water effectiveness, which assesses how a facility electricity use affect the regional water scarcity. And these are being shown in the figure demonstrated here on the right-hand side. So with the literature review, a case study was being made for some vertical farms considering their crop types, the yield, and then the irrigation system, whereby we also consider the specified HVACs that are being used. And then we have the optimal conditions necessary for plant growth in these environmental agricultural facilities. So we consider factors such as the temperature, the relative humidity, the vapor pressure density, as well as the cultivation period for the various selected crops yield. So some strategies to minimize these environmental emissions include the system, whereby we have to consider that artificial lighting and temperature and then the control of humidities contribute to huge energy emissions. So we have to improve the energy efficiencies to reduce this, and also by enhancing the energy efficiency through a better system designs, we can also help to reduce this, and then also investment in the technological methods to also reduce the water and then the energy that these facilities uses. Challenges in assessing the environmental impact of CEA facilities. So we have the lack of the universal standard for reporting these metrics, and also the lack of geographical variability also is also a challenge. And then when there is issue with the sizes, which is the scalability and then the diversity of the CEA facilities. Some predictive tools. So we have the artificial intelligence robust model, which enhances the energy efficiency and reduces the greenhouse gas emissions. we have the deep learning algorithms to improve the real-time energy efficiency, and then the CEA energy modeling, which also recommends that hybrid systems are very helpful in improving the overall energy efficiency of the CEA facilities. So some of the gaps include the geographic variability, the standardized metrics, the lack of predictive modeling, and then the energy source impact. To help address this, the development and the application of the three tools is the main focus of this research in order to help curb these challenges and also solve the various needs of the CEA facilities. The quick calculator incorporates the geographical differences, the standardized metrics is being addressed, and then also the energy source impact, whereby the interactive map looks into the geographic differences and also integration of the local climate and then the power grid data. The power and then the water estimator to integrate the parameters such as the facility size, the crop choice, and then the geographic location. So the overview of the tools. The purpose is to develop a tool to help the facility designers and then operators to mitigate their environmental impact. So here comes the quick calculator, which calculates the environmental burden based on the energy and then the power usage. The interactive map help us to visualize our impact to assess how the location affects the environmental footprint. And then the power and then the water estimator estimate the required amount of energy and then the water usage necessary for the CEA facilities. So the quick calculator, it helps to calculate the footprint and also ranks it to other facilities, similar ones in the US. And then you will be able to visualize the asterisk. It provides you with the climate zone of that particular region. And then based on that, users are able to explore different scenarios. So talking about the benefits, we consider the environmental awareness, the decision support, which offers a valuable insight for reducing the source consumption and then improving the sustainability. And then also the key implication is to identify areas for improvement and also to make informed decisions to meet the sustainability goals. The development of the tools went through three different applications, whereby we have the first, which consists of which the key parameter here to talk about is the Federal Information Processing Standard. So based on this, one has to look for this Federal Information Processing Standard code and then make a calculation for a particular county. So it was further developed to this, and then we have the final version, which provides the additional input fields and also more matrices as compared to the previous ones. And also it is more clearer, and then it has a more interactive interface as compared to the previous two. But after a consultation with the partners, they suggest that it should be migrated into a Google Sheet or Microsoft Excel in this form. So this is basically so this is based on the reasons listed below. No installation will be required, and then also it will help to run the app faster. It will also make it easy to use, and then it will provide the basics or the desired information that will be required. So this is the final tool that is developed using the Microsoft Excel. So how to use the tool? First, enter the power and then the water usage of the facility. Then you select the preferred unit. Based on that, the next thing to do is to select the state and then make a county selection. After that, the output will be generated automatically. Then you see the various carbon footprint, the water footprint, and the water scarcity footprint. I will demonstrate briefly over here how it is being used. So assuming we want to found the impact for a state in Florida, a county in Florida. Assuming we are making let's consider something like Arkansas, and then in Arkansas we don't have Brantford County, so we are going to see not a number in the various outputs, so we need to make the right selection for the right county. So assuming we are considering Clark County, automatically using these hypothetical values, we are going to get our outputs in this form, whereby you have the carbon footprint in the 80th percentile, and then the scope 1 water footprint, and then the carbon water scarcity footprint in the 54th and then the 34th percentile, respectively. So this basically incorporates the FIPS code. In the previous MATLAB version, the system was designed in such a way that one has to input the various FIPS codes, but in this system, the calculator is made in such a way that once the state is selected and then the county is selected, the FIPS code automatically pops up. And based on the FIPS code, the various environmental metrics such as the EW, IF, the SWI, and then the emission factors pops up to help calculate for the various footprints. So the FIPS code is an identical number for each county. So based on that, we are able to find the emission factors and then the various other environmental metrics to aid in the calculation. Okay. So to continue with the presentation, now we consider the equations whereby the carbon footprint is basically calculated considering the on-site power and then the emission factors. The water scarcity footprint considers the on-site water available in addition to the on-site power and then the energy water intensity factor. And then the water scarcity footprint consists of two different sections whereby you have the electricity-based water scarcity and then the on-site water scarcity, which includes the on-site water and then the available water remaining, whereby the electricity-based water scarcity consists of the on-site power and then the scarce water index. So now we move to the overview of the interactive map. And the interactive map helps us to visualize our facility environmental impact across the contiguous UIC. And based on this, operators will be able to compare their geographical impact as a result of their operations. So this is the interface of the CEA interactive map. How does it work? Based on the footprint type, you input the on-site power and then the on-site water, and then you click on the Make Plot button, which will quickly help you to generate your carbon or to generate your plot. And to demonstrate briefly over here, I have my quick calculator already opened. So assuming I want to make a plot for a county like New Mexico, I just click on the drop-down button and then select the type of footprint. Then I click on the state specific drop down and then I select the particular state that I want to make the plot for, and then I input my values, which is the on-site water and then the on-site power, and then the on-site water, and then I make I select the preferred unit choice. After that, I have to click on the Make Plot button, and then it will quickly make a plot for me, which can be zoomed, and then I'll be able to visualize my impacts. I'll be able to visualize my impacts and then to know which part of that particular state will be better enough for this CEA facility to be situated. So now, that's a brief demonstration of the two. So to continue with the presentation, now we move on to why the interactive map. So we said the interactive map will help us to choose sites that will be preferable based on the footprint type, and then also it will provide a transparency when it comes to the facility data impact. So the color binding, so anything between 0 to 33% will give you a minimal impact, a low impact, and then above 33 to 67 will give you a moderate, and then anything above 67 will give you a very high impact. So the power and then the water estimator tool is okay. So the power and then the water estimator tool was made to help us estimate our power consumption in these CEA facilities and then the energy usage. So The system is designed based on the heat transfer methodologies and then the humidity control systems, which will help us for the humidification, then the dehumidifications, and also the utilization of solar energy. In this system, we will consider a hypothetical CEA facility with the various wall lengths. That's the north, the south, and then the east and south and the west. So the area can be calculated considering the length and then the height of the CEA facility. And then for the roof, we consider a symmetrical roof. So the area can be calculated like this, and then the volume for the greenhouse is considered in this manner. And then based on the solar energy requirements, we will consider the declination angle, which represent the Earth axial tilt in relation to the sun's position. And that can be found by this equation, and then the hourly angle, which indicate the sun's position relative to the solar moon. And then that one too is being calculated in this manner. So after that, we can continue with the solar zenith angle. And then finally, we can calculate for the azimuth angle. So the zenith angle is basically the angle in between the zenith, in between the beam and then the vertical walls, and then also the beam projection, the angle between the beam projection and the diffuser, whereby is identified as the solar azimuth angle. Then we have the overall incident radiation, which consists of the diffuse beam, diffuse radiation, the direct, and then the ground reflected. So the diffuse radiation can be found in this, which includes the diffuse horizontal radiation, and then the diffuse radiation factor is also calculated in this manner. So this is the tilt angle, and then this is the vertical tilt angle. So the incidence angle is basically the angle between the beam radiation and then normal to the wall, that's the vertical wall. So the geometric relation of the angle of incidence is shown above, and then the incidence angle can be calculated with this equation, but we are considering a vertical wall. That's where like we consider the tilt angles to be 90. So based on the orientation, these angles are subject to changes. And finally, the solar availability can be calculated considering the direct normal irradiation and then the diffuse horizontal radiation. So the soil temperature can also be found by first considering the heat transfer coefficient, which considers the convective and then the radiative, and it can further be simplified into this manner. And then based on this, we can say that the solar air temperature is calculated below, whereby we consider the ambient temperature and then also the emissivity, the absorptivity over here, and then the long wave radiations are also incorporated. So with the thermal network methods, we consider separate resistances that are being connected in the surface nodes, and then also considering the hourly ambient conditions, basically because we are considering a transient system, and then the internal mass which affect the cooling and then the heating loads. So some of the internal loads that are being considered include the lightning, the dehumidification, the evapotranspiration, and then that of the fans. So with the various nodes, we can calculate the various temperatures at the various nodes as shown below. And then this is applicable for all the walls, that's the south, east, and then the west. But this, we are only demonstrating that for that of the north walls. And then this is also for the north roof, which is applicable for the south roof. And after this equation is being applied to calculate for the sensible cooling load. The use case. So we are considering a facility in Scott County, Virginia specific. And we assume that this facility uses 500 kilowatts of power and then 100 gallons per minute of water. If this is the scenario, then how do the environmental footprint in Scott County compared to an equivalent facility located elsewhere? And if we have a grant, which says that we should reduce the water and then the power usage by 10%. Which of this approach will be very impactful? So in this image, we have the Scott County, which is being demonstrated in red. So after using the quick calculator, the 10% reduction in power resulted in the 10% drop in the carbon footprint, but less than 1% in both the water footprint and the water scarcity footprint as a result of the minimal impact. And then the 10% reduction results in no change in the carbon footprint because it has no impact on the emission factors. But the 10% drop in the water footprint and then the water scarcity footprint. So it also showcased that we had the carbon footprint at the 85th percentile, the water footprint 81st, which is very high, the water scarcity footprint at 22nd, which is relatively low. And then the energy reduction was a key in reducing the carbon emissions, whereby the water reduction was had an influence on the water footprint and the water scarcity footprint. So some technologies were considered by first considering transitioning from a 2.0 micromole per joule to a 3.5 micromole per joule, or EDs. And this was able to cut the carbon footprint by 43%, which also reduces the water footprint as well. And then the nanobubble enrichment system proposed by a consultant was also practiced, and we found out that it was very impactful in the water scarce counties, for instance, the La Paz County. So considering the baseline scenario and then the enrichment system for the carbon footprint, and then this gives us the enrichment system for the water footprint, and then the base scenario for the water footprint. And the final one is the indication of the water scarcity footprint, and then the enrichment scenario for the water and the enrichment scenario for the water scarcity footprint. So now the interactive map use case. So as we want to relocate this facility from Scott County to a different facility, such in Texas, California, or Maine, which of these sites will be favorable, and then in each of these states, which location will be best for us to locate our facility. So in our analysis, considering the carbon footprint, Texas was color-coded yellow, which shows minimal average impacts, and then we have California in green, Maine in green, which all shows a very minimal impact. And then considering the scope 1 and 2 water footprint, we have Texas in green, which shows a low impact as a result of the average grade EWIF. And then California, which is demonstrated in red as a result of the high EWIF, and then Maine is in green as a result of the low EWIF. So we have Texas for the water scarcity footprint in red, the California in red, and then also Maine in green. So based on this, we can finalize that Maine will be an ideal location for us to locate our CEA facility from Scott County. So since Maine will be ideal location, which part of Maine will be very ideal? So when using the case specific, we can say that the lowest footprint can be found in the northeastern corner part of Maine. And then where the power and then the water estimator too, we consider a facility, a hypothetical facility in Miami. So all the conditions have been tailored to the climate conditions and the thermal characteristics in Miami. And then the crop that is being considered here is lettuce. So these are some of the inputs that we consider the plant and then the air properties, the farm properties, and then also the greenhouse wall properties. And also in doing of this, we consider a ventilation requirement of 0.01, which is used. And then as basically it will help like to indicate a limited airflow, and then also making the temperature and then the humidity control much more easier in these facilities. This is basically an information on the HVAC system, whereby we consider the HO, this heating COP and then the cooling COP to be 3 and or other types. And then the final results, we had a power consumption of 35,700 per year, and then that of the water also is being indicated. So after that, these values were fed into the quick calculator, and then these are the impacts. Having the carbon footprints in the 48th percentile, the scope 1 and 2 water footprint in the 31st percentile, and then the water scarcity footprint in the 51st percentile. So based on this, the operators can make decisions, informed decisions on that. To conclude, the quick calculator gives us a 10% drops in the CF when we consider the 10% drop, and also it gives us a 10% reduction in the WF and then the WSF, and we're considering the 10% drop, and then also the interactive map suggests that the eastern part of Miami will be the best fit for us to relocate our facility, and then adoption of the 3.5 micromole over the 2.0 shows that 43% reduction in the carbon footprint, and also states like the La Paz, which has a very high RCF values, which is very scarce in water demands, in water availability, was also indicated by implementation of the nanobubble enrichment system, whereby the power and the water estimator was able to annually determine the amount of power and then the water that will be required for a sample greenhouse in Miami. So in the future, we have to release and then advertise for these tools to be patronized by CEA facility operators. Integration of a user-friendly graphic user interface of the power and then the water estimator to apply these tools to compare environmental footprint for facilities in different climate regions, and then also extend the power and then the water estimator to other CEA facilities, and then also implement a web-based version of these 3 tools to make their use very easy. I would like to acknowledge Dr. Aaron Wemo for putting me on this research, and then also guiding and then advising me on how to go about this research, and also to my thesis committee members, Dr. Sylvia Laurent and Dr. Calvin Lee. I'm very grateful for your time being, and also for your advice. And then to the CEA industrial consultant, thank you very much for your input and also your time being. Then to the Environmental Protection Agency, US, for providing us with the grant to carry on this research. Here are some of their references. Thank you.